Welcome to the Introduction to Limits. I've split these notes into 4 videos. This first one's a bit short, but I wanted to give you the basics of the limits before we started talking about the algebra. In this section, we will develop the concept of a limit. The information developed here is a foundation for an understanding of the next chapter and, quite frankly, the remainder of the course. You should be able to, after all these notes, just demonstrate the definition of a limit by using the graphing calculator, use the properties of limits, compute one-sided and two-sided limits, compute limits at infinity, and use the definition of continuity to determine if a function is continuous. So, the definition of a limit. The concept of a limit is fundamental to understanding of calculus. Previously, we said that a function f is continuous at x equals c if the values of f of x approaches f of c as x approaches c. In this section, we define a limit which makes precise what we mean by approaching. Suppose you're given the following sequence of numbers. So I have 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and I kept going and going and going and going and talking about that. It says, what does this number in this sequence seem to be getting closer and closer to? So if I keep making my denominator larger and larger, it keeps making my number closer and closer and closer to 0, because it's getting very small. It is probably obvious to you that they approach 0. In mathematics, we say the limit is 0. Notation. Okay, the nth term is 1 over n, so the notation, this is how we would say it, as n gets infinitely larger, so we're going to infinity, of 1 over n equals 0. I'm approaching 0. So this is basically, this is what we used to say, all right? As n approaches infinity, my function is approaching, or you can say f of n, my function is approaching 0. That's how we talked about it earlier. All we're switching is we're using the word limit, so they call it lim. Underneath, you're saying as n is getting infinitely larger of my function, and my function is 1 over n, okay? It's approaching 0, so we say the limit equals 0. This line right here means approaches, and infinity is the infinity symbol. The same idea is considered the function f of x equals 1 over x. So here, if we look at it down here, as x approaches infinity, f of x approaches 0, so we can again say the limit of f of x, as x approaches 0, we can say the limit of 1 over x, because that's our function, as x approaches infinity equals 0. So this is just basically a notation. You're going to see, it's going to say limit, and then here we always use our x's for direction. So our x's are approaching infinity, so we're going in this direction in this case. And we noticed that as we're going to the right and our numbers are getting bigger and bigger and bigger, my y values, or if you would be, say, your f of x values, are approaching 0. Okay, so it's just a notation. So let's look at the definition of this. Notice, did I skip something here? Hang on a second. Nope. Okay, so notice the graph of this, of f of x equals 1 over x, has a horizontal asymptote at y equals 0, since the output values approach 0 as the graph goes off to the right. So here's 0, here's infinity. So my x's are going this way. My y values were bigger, but they get smaller and smaller and smaller, so they're approaching 0. So that's what you're looking at, is what is my function doing as I'm going to the right. Now, we want to make this definition in a more general setting. As x approaches a, we can see f of x approaches any specific value, L. So L stands for limit. So we can say as x approaches a, so there is our direction, wherever that wants us to go, of our function. Whatever I come up with that it's approaching is your limit. An important part of the definition, and one that seems to trip up a lot of students, is that x approaching a means x is near a but not equal to a. So approaching means I'm getting closer and closer and closer and closer. So let's do that. When I say I'm approaching, I'm getting closer, that's an O, approaching, I'm getting closer and closer but not necessarily equal to. Suppose a function f of x is defined on an interval around c, except perhaps not at c. We define that limit of f of x as x approaches c as this. All right, so there is the notation again we just talked about. What does this mean? What this means is as we get to f of x as close to L as we want, and we can make x close enough to but not equal to a. So it's just a notation math people use to talk about getting close to some type of number or what your function is doing. Okay? Let's look at some examples. We will look at limits of the form of x approaches a of f of x in three ways, using tables, graphs, and then we'll use algebra. So we're going to do tables and graphs in this video. I'm going to do the next video with the algebra. So this I call the intuitive definition. This is kind of intuitive. What does a limit really mean? So this is our intuitive definition. First, we will find limits using tables. In some ways, this is the easiest method for finding limits. What we need to do is choose numbers getting very close to the a value. If our a is 2, then we might want to choose 1.9, 1.99, 1.999, and so on. We also should choose numbers from the other side of 2, like 2.1, 2.01, 2.001, etc. So here I've got the limit as x approaches 2 of x cubed. So what I did was graph this, okay, and then I looked at my table. Now this table's sideways and the table on your calculator is up and down, and I'm going to show you in another video how to actually get to there. But basically at 2 we don't know what the limit is, but we're going to get really close on both sides. So see how I'm doing 1.9, 1.99, 1.999, and look what our y's are doing, or our f of x. See how it's getting closer and closer to 8? Now if I go to the other side, 2.001, 2.01, 2.1, see how I'm getting closer to 8. So it's like as I come closer and closer to 2 from this side, and from this side I'm getting closer and closer to 8. Notice the limit appears to be 8, which of course we know is directly substituted to 8, so the limit of x cubed equals 8. Now let's look at some trig functions. And the reason why I always look at trig functions is because you have to use radians or they do not work, okay? So remember to use radians, please, 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 okay? So I have the limit as theta approaches 0 of sine of theta over theta, okay? So I'm going to get very, very close to 0. So here's my 0. I'm going to do the negative side. See how I've got negative 0.1, negative 0.01, negative 0.001. See how close I'm getting? And then I'm starting at 0.1, 0.01, 0.001. Look at my y values. Aren't they getting closer and closer to 0? Excuse me, closer and closer to 1. Sorry, this is 0, but I'm getting closer to 1. So we'll say the limit appears to be 1. So that's how we say it equals 1. Okay? Now let's look at some of the graphs. Next we'll use limits using graphs. Again, this is not as difficult a technique, but what we need to do is to graph it and get really close. So I'm using y equals x cubed, so here it is. So I'm getting really, really close to 2. So when we put it in the table, we're doing this, we're getting really close. So if we follow the function, as I get really, really close, what are my y's doing? And if I come from the right, so here I'm coming from the left, here I'm coming from the right. As I follow my function, what are my y's doing as my x gets close to 2? It looks like it's getting to be 8. I'm going to follow from the right, so I'm way up here. What does it look like when I'm getting x close to 2? It looks like it's 8. So by looking at the graph, when I go left to right, my y value is 8 when I approach it from both sides. Same with this graph. If I look at this one, sine theta over theta, remember to use radians. As I approach it from the left, you follow it this way, it looks like I'm getting close to the y value of 1. And if I approach it from the right, I follow my graph this way, and it looks like it gets closer to 1. So you can look at a graph to see what your limits are. So let's find this function. I haven't got it defined, and I want to approach 1. So as I approach this limit, so it says x approaches 1, so I'm going to come from this direction and then this direction. So you have to follow your function. When I approach it to get to 1, it looks like I'm getting to 4. When I approach it this way, it looks like I'm getting to 4. So the limit of this function, I don't know what it's called, is as x approaches 1 is equal to 4. Let's try one more. This graph illustrates a graph without a limit. Notice the functions appear to approach a y value of 4 from the left side. So as I come from this way of this function, and how we say that is this. The limit, as I approach, and this is a 1, and what we show is this little negative sign there. So I'm coming from the left, so I'm going to follow this. See how I'm following it up? Looks like I'm approaching 1, 2, 3, 4. Okay? But there's a hole there, so it looks like it's 4. But when I come from the left, it looks like it's 4. Now watch, I'm going to approach from the right, so I follow my graph down this way, and when I approach it from the right, it looks like it's right here, or it looks like 3.5. How we say that is the limit as x approaches 1 from the right, there's a little plus sign. I forgot to put f of x in here, I'm sorry. Of the function f of x. You always put the function there. Looks like it's 3.5 from the right. Notice the function appears to approach the y value of 4 from the left of 1 and around 3.5 from the right side. In this case, we say the limit does not exist because these two don't match. So when I approach from the left and the right, if they do not match, we say the limit does not exist, and we use D and E. So here is the limit from the left. Here's a limit from the right. So we can say the general limit as x approaches 1 from both sides of this function f of x, we can say does not exist because the left and right do not match. Okay? There's a little introduction to limits.